Swayam Prabha. Digital India. Educated India.
In this lecture, we will continue to discuss about oblique shock waves, and we will also discuss Prandtl Meyer expansion fan. So, last time we had started discussing about the oblique shock. We had drew the velocity triangles. We talked about normal component of velocity and tangential component of velocity. So, we will just quickly redraw that once again. We will also mark the deflection of the flow by an angle theta, the wave angle beta, and you may recall that this is the tangential part, this is the normal part. So, we are using the nomenclature u for the normal component of velocity, and we are using w for the tangential component of velocity. And once you move across the shock, we state the properties in region 2. So, basically region 1 is ahead of the shock, region 2 is behind the shock, and remember that both region 1 and region 2 separately are isentropic regions. The properties vary. For example, the entropy would be higher in region 2 compared to region 1. The velocities, the pressures, the temperatures, they also change, but individually when you look at the regions 1 and 2, they are isentropic regions. The only place where the entropy changes is at the oblique shock itself. So, that is where the jump occurs. Further, we may recall that if we apply the conservation equations to a small control volume that we draw, keeping the shock in between within the control volume, then we should be able to work out the continuity equation and the tangential momentum equation yields the condition that there is no jump in the tangential velocity. The normal component of the momentum gives us the result that p plus rho u square remains conserved across the shock, and finally, the energy equation gives us the result that stagnation enthalpy remains conserved. So, if you look at the continuity equation, the normal component of momentum equation and the energy equation, these equations look identical to the normal shock equations, which means that if we deal with only the normal component of velocity for the oblique shock, then we might as well treat it as a normal shock. So, the normal component of the velocity obeys the normal shock relations. This is a huge convenience because we have normal shock tables broadly under the gas tables. You have a portion dedicated to normal shock tables. So, what do you have in those tables? You will see that the tables contain entries like this, that the first column may be M1, that means the upstream Mach number, second column P2 by P1, that is the pressure ratio, then comes the density ratio. So, these are all tabulated. So, if you look at a specific value of M1, let us say 2, Mach 2, then all these values will be directly available from the tables. P naught 2 by P naught 1, you know that this is linked with the entropy rise across the shock. Then you have P naught 2 by P 1, you have M 2. So, all these would be available from your normal shock tables. So, if you can get these values from the normal shock tables, you just look at the normal component of the velocity coming from the free stream side and do the calculations accordingly using these tables, and you are done with the calculations basically. Once you are done, what you can further do is, let us say when you look at M n 1, that is the normal component of the Mach number. So, this is the first thing you work out. For that, what you need? You need the wave angle. All right. And once you are done with that calculation, you can plug it in to the equations that you have for normal shock. So, only thing is that instead of M 1, now you are calling it as M n 1, which is being plugged in. Similarly, pressure ratio can be worked out in terms of M n 1. What about the M n 2? That is given by this relation, and obviously M n 2 will be less than 1. M n 2 will be less than 1, because when we are talking about the normal component, it is equivalent to a normal shock situation, and across the normal shock, once you go beyond the normal shock, the flow becomes subsonic. Therefore, M n 2 has to become subsonic. If you are interested in temperature, for example, you can make use of the equation of state and use the above density and pressure ratios to work it out. In order to get M 2, not the M n 2, but rather M 2, you have to use the equation M n 2 by sin beta minus theta. So, if you look at the geometry of the problem, you can make out very easily why beta minus theta comes in here. So, this is your M 2, this is your M n 2, and this entire angle is beta, while this portion is theta. That means, this is your beta minus theta, and therefore, from the geometry you can work this out. So, we now find that in normal shocks, the flow properties were only a function of M 1, the upstream Mach number, while for an oblique shock, what is happening is that the property changes, they are a function of both M 1 and beta. The beta comes in here, because you are basically using the normal shock relations here, and therefore, M 1 and beta, both of them get into the calculations. So, this is one deviation in the calculations. There are some more observations, but before that, let us look at another very important relation which connects M 1, beta and theta. So, there is basically a connection between these three parameters. Without deriving it, we are just stating the final relation. So, this is the relation. So, this is popularly known as the theta beta m relation, and if you make a plot where you have the theta along the horizontal, beta along the vertical, then you will find that you will get curves of this kind, where the parameter that you are having for these different curves is basically the Mach number. Let us say this is a fair enough high Mach number, say Mach 10, this is Mach 5, this is Mach 2 and so on. Then for each Mach number you have a maximum theta, we call theta max, for which you will get a solution where the shock is going to be a straight oblique shock. What do we mean to say? Let us say we take a compression corner like this and we draw the oblique shock like this. So, this is a straight oblique shock which is emerging right at the compression corner. Could there be a case where the shock gets displaced from here and it becomes a so called detached curved shock? Well, yes, it is possible. Let us say you are talking about a theta here which goes beyond the theta max value corresponding to a particular Mach number, then this is what is going to happen. So, for each Mach number you have a corresponding maximum theta for which you can have a straight oblique shock solution. If your theta happens to lie below that, then there would be two Mach numbers at which, or rather two wave angles for that particular Mach number where solutions are possible. So, let us say we are looking at a particular theta here and we are talking about a Mach number 5 coming from the free stream side. So, you have two solutions on this curve which satisfy the conditions, all right. So, the one with the lower beta is what is called as a weak solution, while the larger beta is a strong solution. Strong shock solution and weak shock solution. So, that is how we will like to specify it. Okay. So, higher the beta, stronger is the shock. When would these situations arise at all? Well, these situations can arise based on what kind of pressure is maintained downstream of the shock. So, we call this as a back pressure. So, you could have a situation like this, that you have a low enough back pressure, you have a certain m1, you have a certain defined theta which is less than theta max, and you have two solutions, two betas, all right. So, obviously, from this plot you can now correlate that which is the weaker shock, which is the stronger shock. So, that is left for your thinking. So, we showed a possibility of a so called detached curved shock, and I have already mentioned in an earlier lecture that the flow behind a curved shock is rotational. So, that is also something that one has to keep in mind. Let us say instead of being a compression corner, this was happening for a flow past a wedge. how would a detached shock look like in the case of a wedge? This is how it will look like. When it remains attached, it looks like this. So, the attached shock solution means you are lying well within these curves corresponding to the Mach number that you are talking about, and the moment you are detached, you must have gone beyond the theta max. So, this is the interpretation that we get from the theta beta m plots. So, when you have a strong shock solution, you have to remember that the M2 becomes subsonic. So, we are not talking about Mn2, by the way. Mn2 is always subsonic, but here we are talking about M2. So, that also can become subsonic in the case of the strong shock solution. And further, let us write down another aspect, that for a fixed deflection theta, as the free stream Mach number decreases, the beta increases. So, we are not changing theta, mind it, we are just changing the free stream Mach number, we are decreasing it. At the same time, the beta starts increasing. So, that means there is a lower limit of Mach number for which the shock will remain attached. So, if it goes any lower, if the Mach number goes any lower, then the shock detaches. This is a very, very important information that one has to keep in mind. Since we are talking about a two-dimensional flow problem here, when we are discussing oblique shocks, there is another very interesting way of representing facts through what is called as the shock polar diagram. So, we plot the x component of velocity along the horizontal, the y component along the vertical, and let us say we are showing the x component of velocity upstream of the shock using this arrow, and the velocity downstream of this shock by this arrow. So, this is basically V1, this is V2. So, this is for a particular theta, for a particular deflection, and that deflection must be given by this angle. So, if you change the deflections for the same V1, you end up getting V2s which are inclined at different angles, and also the magnitudes of V2s start changing, because the shock gets stronger if theta increases for a given V1. So, that information, how would you plot it? You plot it in the form of a shock polar. So, you end up getting a locus of points like this, which may look more like this, and then what you are doing is you are basically taking these points and you are plotting to generate this locus, which basically means that you are looking at different thetas, what the solution looks like. So, the V2s corresponding to the different thetas are actually giving you this locus. So, that forms what is called as a shock polar. So, with that we come to the end of this discussion on oblique shocks. We will revisit it once again when we discuss about the shock expansion theory. So, now let us discuss a little bit about Prandtl Meyer expansion. We had briefly discussed about it earlier. So, the surface over here is turning away, and therefore, it is going to expand the flow. Of course, both the Mach numbers in the two regions before and after the expansion are supersonic, but since it is expanding, it is accelerating. Also, if you look at pressure, it is reducing, temperature, it is reducing, density is reducing. It is an isentropic process, and therefore, entropy remains identical. If you look at the stagnation pressure, for example, it must remain identical, because it is an isentropic process. Stagnation density also remains identical. Of course, stagnation temperature certainly would, because for stagnation temperature conservation, you just need the process to be adiabatic, no more than that. Here you have reversible adiabatic. Now, these angles are very special. This angle is mu 1, the other one is mu 2. We have discussed them earlier when we talked about Mach waves. So, we will call this as the forward Mach line. So, that Mach line has an association with the upstream Mach number. You have a rearward Mach line which has a connection with the downstream Mach number. Therefore, obviously, mu 2 will be sin inverse 1 by m 2 by definition. Now, we go to a relation which gives you a connection between a differential change in the angle of inclination of that surface. So, if it is a differential change, if it is a small angle d theta, then there will be a small change in velocity downstream. Obviously, the velocity will increase, but there will be a small change. Now, if that angle is not differential, but rather it is a finite small angle, then you have to integrate that relation, and then finally, after you do, you will come up with the so called Prandtl Meyer function. Let us have a look at the function, what you get. So, that function nu is defined as an integral of the local Mach number So, this is the integral which gives you the so called Prandtl Meyer function. There are tables of the Prandtl Meyer function where the upstream Mach number, the nu and the mu values are given. Now, once you integrate that, it can be shown that the final relation comes out like this. Which is rather easy to evaluate. Even if you do not have the tables, you can do it with your own calculators, as long as you know the Mach number. Further, when we do not have a differential change in the angle, but rather you have a finite change, let us say we call it as theta 2. So, that theta 2 is given by the value of the Prandtl Meyer function in the region of Mach 2 minus the value of the Prandtl Meyer function in the region Mach 1. That means, this is the downstream side value of the function, this is the upstream side value of the function, and the function itself is given by this equation. Therefore, you can work out those functional values. Now, let us try to find out the steps that we would like to take, the steps for calculations. Let us obtain nu m1 either from this equation or from tables for a given m1, that means the upstream Mach number. That means this value is now available to you. Now, based on the geometry, which means the theta 2, you know what is nu m2, right, because nu m2 is nothing but theta 2 plus nu m1, which you know already, this comes from your geometry. So, you know the value of this. You can go to the tables and you can work out for what value of m2 is this value of nu coming from the tables. So, obtain m2 from the tables. Once you obtain the m2, your job is practically done, because now you are going to just use the isentropic relations between states 1 and 2 to find out the properties in region 2. All right. So, let us write down typically two relations which may be useful that way. Let us say temperature ratio, it will be obtained by an equation of this form. So, this is coming from your isentropic relations. If you are interested say in pressure, you can again use the isentropic relations. Only difference is in the index, as you can see. That means, all the properties, all flow properties in region 2 are now easy to obtain. Which means, basically you have solved the flow field across a Prandtl Meyer expansion fan. Now, what kind of application can you look at once you have done this problem? Well, you can look at a very useful application, that is in supersonic flow fields. If you put in a lifting surface, then what kind of forces are going to act on it? You can plug in the understanding of oblique shocks and expansion into a theory which we often call as oblique shock and expansion theory, or simply shock expansion theory. How do we work it out? Let us see. So, the flat plate which has a chord length say c is immersed into a supersonic free stream which is approaching it, and we have an angle of attack alpha here. All right. Now, look at the inclination of the surface. It is such that on the lower surface it will create compression, and therefore, there could be an oblique shock, provided that the theta is less than theta max. Here that happens to be alpha, because the compression is being produced by this angle, which is alpha. So, alpha has to be less than the theta max corresponding to that particular Mach number m1. As long as that happens, you have this as the beta. This is the wave angle. While on the upper surface, the flow is turning away, and therefore, there will be an expansion fan. That means, the flow expands. And then you would have a lower pressure on the upper side compared to the lower side, because on one side it is expanding, the pressure is dropping, on another it is getting compressed because there is a shock, and the pressure is uniformly felt on the upper and lower surfaces. Let us name the regions. This is region 1, say this is region 2, 3, free and so on. So, in that case what you have is, because of the pressure distribution on the upper and lower surfaces of the plate, you have a resultant force R, and that acts on an area C into 1, right. So, that is the resultant force, which will be normal to the plate. Now, if you resolve it into components, you clearly see that there is a lift, but as well there is a drag, and this is the wave drag that we talked about. This drag is the wave drag. Of course, you can resolve R into components and work out what that wave drag is, but it is happening because there is increase in entropy across the oblique shock. What does that do? What does that do? That leads to loss of stagnation pressure, and that is reflected through a drag force. So, though the flow is inviscid, mind it, but still we see a drag. How do we get drag? Of course, we just have to take a component of R. So, it will be P 3 minus P 2 C sin alpha. Of course, as alpha becomes smaller, the drag also becomes smaller correspondingly. Lift is worked out like this. Of course, they are per unit span. This is how you would work it out. Okay. So, we saw the application of shock expansion theory here, but the story is not over. The flow, before it leaves the plate, there will be a compression here, because the flow approximately turns parallel to the incoming free stream, and while it turns, there is an oblique shock formed here. On the lower surface, it expands to turn that way, and therefore, there is an expansion fan. So, there is a trailing edge expansion fan on the lower side and an oblique shock on the upper side. So, there was an expansion fan here at the leading edge and an oblique shock at the lower side, right. So, this is how it works basically. So, in this lecture we discussed about oblique shock and Prandtl Meyer expansion. Further, we discussed about how the concepts are useful for calculating supersonic flow past a flat plate using the so called shock expansion theory. Thank you.